Saxon Advanced Mathematics Lesson 118, Roots of Polynomials. This is an extension of the lesson we learned yesterday, 117, which was about rational roots theorem. What that lesson taught us is that if you have a polynomial that's bigger than a trinomial, right? Its highest exponent is bigger than 3. We don't have any easy way, like the man-eating dragon or completing the square, we don't have any easy way to quickly factor that. But what we can do is we can use the rational roots theorem to come up with a list of possible rational roots. All of them are not going to be the roots. It's not like that. We have to sort through the list and test them. That's what we're going to work on today. But we also have to recognize that if this is a polynomial that only has complex number roots or irrational roots, we're not going to find them. This only works for finding rational roots. So it still doesn't guarantee. It's not a strategy that works for all polynomials. It only works if it has rational roots. And P.S., we can't tell by looking at it if it will have them or not. All we can do is dive in and test them. So let's take a look at how that works. First problem, here's the polynomial. John asks us to find the roots of 2x cubed plus 3x squared minus 7x minus 3 equals 0. Again, let me just stress, all we can hope to do is find the rational roots. If this doesn't have rational roots, we're stuck. We don't have a tool yet for how to manage polynomials that have roots that are complex numbers or irrational. But that's okay, we're just gonna hope for the best. Okay, we remember that the first thing that we do is we create the list of the possible rational roots using the rational root theorem. We're not going to write that all over again, right? What is the rational root theorem again? Oh, well, don't worry. I've got it right here. The rational root theorem is we take the integral factor of the constants over the integral factors of the lead coefficient. So we're paying close attention to the constant and the lead coefficient. This will be the numerator because we put the constant factors on top, and this will be the denominator. Okay? So I'm going to write down the rational roots theorem again because I want you to have it in your notes in front of you. Rational root theorem, and again we write an integral factor. Don't worry about the word integral, we'll get to that later, of the constant, and there's the constant, and that's why I wrote numerator by it, is because that's the number that we're going to address in the numerator. And then in the bottom we have an integral factor of the lead coefficient. And that's why I wrote denominator there. That's the number that goes in there. Okay, so we have to consider all possibilities of the factors. Again, that word theorem doesn't rattle us because we know that's for more complicated situations. John's giving us cute little baby numbers. So what about this constant in the denominator? Let's see, it could be plus or minus 1 plus or minus 3, right? It's a short list because there's only 2 factors of 3, and that's 1 times 3, and that's all there is. If it helps you, we can write this out as 1 minus 1, 3 minus 3. Whichever helps your brain work better. The denominator, it's just going to be 2 and 1, right? So plus or minus 1, plus or minus 2. And again, that will be 1 minus 1, 2 minus 2. Now we are ready to write out all the possible roots. And remember last time, we know that it's fair, you have to be fairly careful, starting with this one, going down and across, this one, make sure you have them all. There's a fair amount of duplication because 1 over 1 is the same as negative 1 over negative 1. So we can simplify. We don't have to write the same number multiple times. But I'll just make a list of all the different numbers. There's 1, there's minus 1, there's 1/2, there's minus 1/2. Now I'll try the 3's. There will be 3 and minus 3, and then 3 over 2 and minus 3 over 2. And then again, we can also write this as a plus or minus 1, plus or minus 1/2, plus or minus 3, plus or minus 3 over 2. Whichever version of this process and this process works in your brain the best, use that, all right? It doesn't matter which you use as long as it feels good in your brain, all right? So this is where we stopped at the end of the problem in lesson 117 yesterday. We just made a list of all the possible rational roots. Now we're going to test them and narrow down the list. Okay, how are we going to test them? Oh, our friend's coming back for yet another purpose. We're going to use synthetic division to test them. Now, the sad news is, here, I'm going to copy the short list. Plus or minus 1, plus or minus 1/2, plus or minus 3, plus or minus 3/2. The sad thing is we do have to test pluses and minuses. We can't, just test like +1 and say, oh, -1 would be the same thing. No, it doesn't work like that. We have to test them separately. The good news is we can stop as soon as we get a remainder of 0. We don't have to do them all if we stumble upon the answer early. And there isn't, as far as I know at this point in my life, there's not an easy way to guess which one of these roots might give us a remainder of 0. But this is really great news because we don't have to keep going and do them all. 2, 4, 6, 8. That's 8 synthetic divisions. But if we get a 0 on the second one, woohoo, we're done. So we're just going to jump in and start doing synthetic divisions and see what happens. So let's start with 1. We're going to divide by 1. We need our original polynomial, which is here. So I'm going to copy these coefficients. We would have to fill in any gaps, but that's okay. I don't see any gaps here. It looks like we've got them all. So it's 2, 3, minus 7, minus 3. We'll use that pattern for all of them, right? The coefficients won't change. We just have to keep calculating. We bring down the 2. 1 times 2 is 2. We always add. 1 times 5 is 5. And what I like to do is just circle my answer because that's where I want my attention to go. If I can get that to be 0, I'm good, but it's not. So let's do -1, right? I'm just going to go positive, negative, positive, negative. 2, 3, minus 7, minus 3. If you feel like you're not all that adept at synthetic division, oh, this is going to give you lots of practice. Bring down the first number, then start multiplying, and then adding. -1 is a no-go as well. Okay, let's try, we'll just go ahead and do the 1/2. So I'll show you the fractions don't hurt. The fractions can lead to slightly more complicated calculations, but it's nothing that's going to hurt too much. 2, okay, so 1/2 times 2 is 2/2, which is equal to 1. Oh, that's nice. 3 plus 1 is 4. 1/2 times 4 is 4/2, which is 2. Again, it simplifies. Okay, that becomes -5. Okay, now this is a little messier. This becomes -5/2. And honestly, you could stop right here and go, that's not 0, so I don't even care. But I'm going to go ahead and change this to -6/2. And so we get for our final value, our remainder, -11/2. That's not 0. Okay, let's try -1/2. 2, 3, -7, -3. See how I just keep copying the coefficients as if it doesn't hurt at all. 2, okay, now again, this is going to work out nicely. -2/2 is -1. This is 2. Look, we got it again. This is -1. This becomes -8. Okay, -8 times -1/2, that becomes positive 8/2. That's positive 4. Oof, we're close, but still, that does not come out to what we want. Okay, so we've done all of these. We've done all of these. We're now up to our 3's. Same coefficient pattern. 2, 3, -7, -3. Three times 2 is 6. 27. That didn't work out. Dang it. We keep going. This I'll try the -3 over here. 2, 3, -7, -3. Like I said, it would be nice if I could give you some hints as to which ones to try first, but I don't have any good hints for you. We just have to tackle them. Okay, -6. -3 doesn't work either. We've tried all of those. All right, let's try +3/2. It's going to be another multiplying challenge, but that's all right. It worked out pretty well the last time, right? The 1/2s weren't horrible. 2, 3, -7, -3. Ready? 3/2 times 2. Well, the 2's would cancel, so that would leave us just a 3. This becomes 6. 6 times 3/2 would be 18/2, which is 9. -2. Okay, now oh no, this is +2. There we go. 2 times 3/2, well, the 2's will cancel, and this would be a +3. And look what glorious thing just happened. We found that +3/2 seems to be a rational root of our original polynomial. So how do we write it? What do we do with that information, right? Okay, so I'm going to change my sentence to make it simpler. We're going to rewrite the factored polynomial. Okay, we know that this not only proves that it checks out, but then these are the coefficients on what's factored. So we can say that our polynomial now can be written as, this is positive, but we know it will be x minus 3/2, right? Because the sign always flips when you write it in this form. When you take the answer and you write it back as a factor, we need to change the sign on it. And then this will be, let's see, remember these are going to be the coefficients, but where's my original? We won't have a cube term. This will be our x squared, and this will be our x, and this will be our constant. I could have also written a, b, and c, couldn't I? Because that's another thing here. I don't want to use that color today. These are the coefficients that go on the terms of the quadratic that we'll have left. So it's going to be 2x squared plus 6x plus 2 equals 0. See how I did that? I took this and wrote it as a binomial factor, and then I took what we calculated and wrote that as the other term. Now what we want to do, this looks good, right? This is done. That's all factored out. Now what we want to do is see, can we factor this using, because now this is a trinomial, right? So now we can use our old methods, right? If we have it in this form, then we can factor it maybe by inspection, but certainly by completing the square or using the man-eater, right? So let's see what we can do to factor this a little bit further. I personally think that, so now I'm just looking at this much. I'm leaving this alone. We'll add that back in at the end. I'm just looking at this. I'm going to pull out that 2. X squared plus 3x plus 1 equals 0. Okay, this will just come down. I'm only factoring this part. Now, can we possibly factor that by inspection? Are there two numbers that multiply to plus 1 and add to 3? No, that's not going to work. So we're going to use the man-eater on this. If you haven't heard my story, one of my students many years ago once drew an elaborate, he was an algebra student, he drew an elaborate picture of a dragon breathing fire on the whiteboard that we used for class, and the fire in his mouth came out kind of like a speech bubble, you know, like in a cartoon or a graphic story of some sort. And I said, what is the fire-breathing dragon saying? Or what is the man-eating dragon, we were calling him. And my student smiled, and then he wrote this in the fiery air bubble coming out, speech bubble coming out of the dragon's mouth. So that's when we started calling this the man-eating dragon, or the man-eater. Because that's what the fiery dragon on the whiteboard said. So what we're going to do is we're going to use this to solve this. We're going to need some values for A, B, and C. A is 1, B is 3, C is 1. Remember that when you use this, you should always use buckets. Because when we have potential minus signs on our values and then minus signs in our equation, that, my friends, is a recipe for true disaster. Make a fire-eating dragon look like a marshmallow. So we want to put buckets in for every letter. And then we fill in the buckets with the values. A goes here and here. B goes here and here. And C just goes there. Now we're ready to simplify. I always do the pig house first. Radicals behave like pig houses. Story of the Three Little Pigs. It's amazing how many details actually work. 3 squared is 9, minus 4 equals 5. So 5 will be the simplified number in the pig house. X equals minus 3 plus or minus the square root of 5 over 2. There are two ways to write this. You could draw a single line and put 2 over the whole thing. I'm going to use the more specifically mathematic precision model, and I'm going to make them separate fractions. The reason why is because this is a rational number, but this is it's rational, but it's got an irrational denominator. So we just kind of want that to be separate. So now, this is the factored form of this, and here, I'm going to do this so we can see all 3 pieces together. Okay, so we're looking at this. This would be x minus 3/2 equals 0, right? If we're using zero factor theorem to solve for this. X could equal, and John writes them out. I'm going to go ahead and write them out. This one would be first. That's the first option. If x is 3/2, this turns to 0 and the whole thing is solved. We don't have to consider this 2 because there's no way that the 2 can turn into a 0 and flip this whole thing. So the 2 we can ignore. And then we've got these two values. I'm going to write them separately. It could be, minus 3 over 2 plus square root of 5 over 2. Or it could be minus 3 over 2 minus square root of 5 over 2. So this is the best, most complete, orderly, and perfect way to write that. We used, just to remind you of what we did, I'm trying to find the page where this all began. Here it is. We started with this polynomial. We made a list of the possible rational roots using the rational root theorem. Here's our list written in a couple different ways, right? Here's where we were writing out the factors in fraction form, and then we simplified here. Then we had to test the little buggers, didn't we? And that took a whole page. We did stop as soon as we got to a remainder of 0, which was down here, and then we used these coefficients and this number to create this expression. We knew that 3 over 2 was a rational root, so we wrote that thusly. And then we used these coefficients to set up the rest of what was left of the polynomial. Then we pulled out the 2 because that was annoying. Then we used the man-eater to factor this. We got these two, it's 2 roots, right, because it's plus or minus. We got 2 roots that satisfy this part, and then we have our original one that was the 3/2. And here I have written them all in line. Woo! That was a lot, wasn't it? It was, and there's still one more problem for this lesson. See, I've drifted way out of camera, haven't I? All right. Find the roots of x to the third plus 2x squared plus 6x plus 5 equals 0. I want to point out that John is being kind. He's giving us polynomials, but they are just cubes. He's not going like, up into the power of 14 land. Okay, so first we list our possible rational roots. We use, my marker was on the floor. Somehow my marker's always up on the floor, and my caps, these little caps that go on my markers, they're always on the floor. It's a problem. This is going to be, the factors of this number are going to be in my numerator, and the factors of this coefficient, which I have to draw in, are going to be in my denominator. Remember that technically we call them the integral factors, but because our numbers are nice and simple, the word integral isn't really important yet. Okay, so what are our possible factors of this one? Well, this is pretty easy. Plus or minus 1, plus or minus 5. These are prime numbers, right? So we don't have a lot of options. And this is just plus or minus 1. So that means that when we simplify this, it can be plus or minus 1, or it can be plus or minus 5. That's all. There aren't that many options for us. So now we will start checking. So this is one list possible rational roots, remember that we're only listing rational roots, and if there are complex numbers or irrational roots, we're not going to find them using this. But we are using our rational roots theorem, numerator, denominator, that whole thing, to come up with this list. 2, we have to divide to test them. Again, as soon as we find one that comes out to a numerator of 0, we can stop. So let's just go in order. Okay, let's start with number 1. And what are our coefficients? 1, 2, 6, 5. I like to be able to squeeze in 2 columns. This is a little crowded because I'm writing steps down here, but we'll see what happens. 1. 1 times 1 is 1. 1 times 3 is 3. 1 times 9 is 9. 14. Dang it. That doesn't work at all, does it? Okay, let's try negative 1. 1, 2, 6, 5. I like to try and keep this as neat and orderly as possible so that I don't go crazy. This one, we don't have that many to test, but like in that first problem we did, we had a lot of things that needed testing. It gets messy and crazy and confusing. So I try to be really orderly and step by step, right? I try to lay it out in a way that will help me keep my place and not get confused. Okay, we bring down the 1. Minus 1. Minus 1. Minus 5. Oh, look what just happened. It's so exciting when it happens, right? So that tells us that this number, this minus 1, is a factor of this big honky binomial. Now remember that when that's the root, so we can say that x equals minus 1. That's our rational root. So when we want to put it back into the polynomial, we flip the sign and it becomes x plus 1, right? Because that's how we would get x equals minus 1. We'd swim that across. Times, and now we're going to use these coefficients to set up what's left after we factor that out. It will be x squared plus x plus 5, and all that equals 0, just like this. So what we've done, just to say it one more time, is we started with this 3rd degree polynomial. We found a number that is a root, so we wrote that as if we had factored out the binomial, which we did, and then we used the rest of our division to set up the remaining polynomial, because we're dividing, so it makes sense, right? Now we have to solve this part. Could we factor this by inspection? 2 numbers that multiply to 5 and add to 1? No, that's not going to happen. So here comes our man-eater again. 1, 1, 5. Oh, he's on the other side. It's x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Generally, my rule is that you need to have the formula in front of you. Here it is. You need to have the formula on the page in front of you. And if you don't see it, you need to write it down. I'm bending that rule for myself because I write super big and because I've written, your hands are going to break off, right? So here it is again. And now we plug in. A goes here and here. B goes here and here. C goes there. And it is positive 5. Let me double check. I see this kind of messy little squiggle here, and I'm like, I don't know what that means. I better check my value. And it's positive 5. Okay, so now we simplify. It's 1 minus 20 equals minus 19. Oh, okay, that's kind of creepy. There's a complex number, an imaginary number just waiting for us. So now we get x equals minus 1 plus or minus the square root of 19. I, remember the I for imaginary sits outside of the pig house. It doesn't go inside. And then we'll put these over 2. Remember that when we have an imaginary number, it's very important that we keep the fractions separate. We always want to protect this notation We do not want to combine our real number with our imaginary number. So here it's very important. And that is why in problems like this, I mean, technically we could connect them, but we're just being careful to protect that separateness just as we do with complex numbers. So that's why I'm on team separate fraction. Okay, last step is to write this all out. We have 3 values for x that will set this polynomial to 0. Either x plus 1 equals 0, right? We're using 0 factor theorem now. Either this has to go to 0 or this has to go to 0. The only way this can go to 0 is if x equals minus 1. And then we've already figured out these are the values of x that will set that to 0. The man-eating dragon doesn't take us to a factored form. It takes us right to our roots. Here, we know that minus 1 is the root because we saw it there, but then we wrote it back into factored form, so now we're putting it back into root form. So we say our final answer is x may equal minus 1, or it can be minus 1/2 plus square root of 19i over 2, or it can be minus 1/2 minus square root of 19i over 2. Whew! No wonder we couldn't just look at it and see that, right? But our rational root theorem and our synthetic division are helping us so much. This is right. Did I smiley face my other one? Yes, I did. Got them both right. All right, so that is lesson 118, and that is using rational root theorem to find the roots of polynomial equations. I didn't write that there. I suppose I could, but you get it. It's with equations. You can't find the roots of expressions. You can only find the zeros of expressions. That's a lesson we had recently too. Okay, lesson 118 is done. Yay, thank you, goodbye.